All right, hello everyone. So today we're going to continue our discussion of the periodic table, pointing out some features that really sort of detail why it is arranged the way that it is, and how we can tell information about elements based on just where they lie on the periodic table. So the first thing we're actually going to discuss are those other two models of the atom, the Bohr, and then finally the Schrodinger model of the atom, which is the one that we sort of take to be truth to this day. But before we get into that, we actually are going to discuss a little bit about the nature of light real quick. So light travels in waves. These waves, actually, first of all, one of Bohr's famous contributions was this idea that light travel, and actually I think Einstein gets a lot of credit for this too. Anyways, this idea that light actually was made up of particles just like atoms and electrons and all that good stuff. Light is its own type of particle known as a photon. Okay. And these photons behave a lot like waves. So they have two characteristics that are really important, and they're kind of related. The first is wavelength. So you can see we got two different waves here, and you can characterize them by their wavelength. That is, from peak to peak, how long that is. That would be measured in something like nanometers or meters or some other length measurement. So this would be an example of a long wavelength compared to this one over here, where it goes peak to peak in much shorter distance. So this should be a short wavelength. Okay. And this is, so this is just one of the properties that we can use to describe waves or, photons, for example, is what is their wavelength? Inversely related, but it's basically kind of the same piece of information, is this idea of frequency. And that is in a given period of time. So let's say that this is 1 second here, this distance. This is how far this wave travels in 1 second. How many cycles does that wave go through? So you see that our long wavelength wave goes through 1 cycle. So this would be a relatively short, let's say small frequency. But our short wavelength light goes through many different cycles, 1, 2, 3, 4 different cycles in that same period of time. So this would have a large frequency. And so these are these two characteristics. Again, they're basically giving you the same piece of information, and they're inversely related. A wave that has a long wavelength will have a small frequency. A short wavelength will correspond to a large frequency. Okay. So anyway, these are just two characteristics that we use to talk about waves. And importantly, the reason wavelength kind of makes a little bit more sense intuitively, I've always preferred wavelength. The reason that frequency is used also is because it's proportional to the energy within that photon. So as the frequency increases, the energy within that photon increases as well. Okay, and so all light, all photons fall on what's called the electromagnetic radiation spectrum. So electromagnetic radiation is just kind of another way of saying photons, another way of saying light. And that's, yeah, so, and it can fall anywhere on this spectrum. Actually, this slide's even better. It really gives you the breadth of what that spectrum can be. When we're talking about radio waves, we are talking about photons or electromagnetic radiation that have really large wavelengths. Oops, I'm large. Right? So your AM or FM radio is shooting out radio waves that are basically just photons. That's all, I mean, it's not basically, that is what they are. And they're very, very long, which is why those photons don't have any trouble penetrating, say, the walls of a building, or can get into your car. On the sort of other end of the spectrum, we have something like gamma rays or X-rays, or probably an even more commonly known one. And these are really short wavelength of photons. Okay. And then sort of anywhere in the middle, notice how this is, there's only like this small sliver right here that's considered to be the visible spectrum, right? And so really what we call light versus X-rays versus radio waves is really just that small portion of the electromagnetic spectrum that we can actually pick up with our eyeballs. That's what light is to us, is what we can see. If we had even better, cooler eyes, we could see, for example, infrared light, which is, what a heat lamp gives off. So, you've heard of infrared goggles and how you can see something like a bear or something in the woods in the pitch black if you have on these goggles. That's because it's picking up a sort of longer frequency of light. So if we had really super duper eyes, we could see everything from X-rays to radio waves flying all around us. Probably be really confusing and wouldn't be very much information. But anyway, so we've evolved to be able to see this very narrow sliver here of the EM spectrum. Okay, so this was sort of one of these fundamental things to the discovery of what's called the Bohr model of the atom, which is a little bit more sophisticated than what we left off with last time. So these are an example of line spectra, and actually B here, this is like from the sun, giving you all wavelengths of light, right? So the sun is what we call white light. It's composed of all the different frequencies that make up what we call the visible spectrum. One of these fundamental things for the development of these new models of atoms was this discovery that if you took, say, a sample of this one right here would be hydrogen gas, and you took like a tube of hydrogen gas and you ran electricity through it and you looked at the photons that were being emitted, you would find that only a very select few would actually be emitted from this sample of gas. You wouldn't get every different possibility. In fact, you only get 4 specific photons that would be emitted within our visible spectrum. These are going to be different elements. To be honest, I don't really know which one's which. I know sodium is pretty common. I guarantee you one of these is sodium. The other one's another element. But basically, there's this discovery that if you take each individual element and you run electricity through it, you do what's called excite that atom, it will start emitting photons, but it does so at very, very specific frequencies or wavelengths, right? So you don't get some broad spectrum like you do from the sun. You get very discrete photons that are being emitted. The bigger the atom, the more complicated these spectrum look, the sort of like more lines you actually get, right? So hydrogen's the smallest atom. It has kind of the simplest one with 4 lines. As you get bigger and bigger, you start getting more lines. Okay, so if you remember last time, we left off with the Rutherford model of the atom, which was just simply that an atom has a dense nucleus that consists of protons and neutrons and has electrons that zip around outside of it. Bohr basically came along and said, yes, that's all true, but these electrons are sort of sitting there orbiting at fixed energy levels. Okay, so each one of these rings here represents a different energy level that electron is kind of trapped in. Okay. And this all came for this idea. I actually think it was Einstein that sort of first said that light is quantized into photons, and he took this idea and ran with it around the same time. But he developed this model of an atom that looks like this. Okay, so let's just sort of, this is sort of a bit more complicated of a picture than what we just saw, but it's the same sort of idea. You have these different energy levels, n equals 1, n equals 2, n equals 3, and the electrons live at these energy levels, right? So I might have 2 at this n equals 1 energy level, and then maybe 3 at n equals 2, et cetera, okay? Just some terminology here. These quantum numbers, n, they correspond to that energy level, and as we'll see, they have to do with sort of the size of those orbitals. The other term to note is that energy level n equals 1, that's what we call the ground state. Okay. And I'll go back to this fourth fact here in a second, but this is kind of the deal of how Bohr came to this conclusion that these line spectra indicate this model of an atom. So the idea is that when we have an electron, or when we have our atom, and let me just sort of point out here that this circular n equals 1 corresponds to this n equals 1 on this more line graph. Here, this next ring, n equals 2, same sort of thing, that's this n equals 2. And this is just the reason that we would use maybe this picture on the right is it's a little bit more straightforward. You have energy on the y-axis, and then you just have these different energy levels, okay? So Bohr's theory was that you have an electron that's sitting at, say, the ground state. And what happens when you run electricity through that sample of gas, is you actually kick this electron up to an excited state, up to a higher energy level. And then it will relax back down, back to the ground state. And when it does so, it will emit a photon. Okay, so the reason that that spectrum for hydrogen just had those discrete lines is because there are a limited number of these energy levels. So one of the photons would be corresponding to this, maybe another one, you know, from this 1 to 2 transition. Maybe you'd have another one that corresponded to this transition here, another one to this transition here, et cetera, et cetera. And each one of those would produce a different frequency of light because those energy levels are different. Okay. It's actually, he really wasn't too far off. We think about it a tiny bit differently than how he had originally theorized it. But this idea of electrons living in energy levels is very much so a thing. We can actually now have modern instrumentation that can watch either what's called an absorption, which is when a photon is absorbed, promoting an electron from lower to higher. So this transition from 1 to 2, this would be an absorption of a photon. Or, right, so an absorption. Or we also have instrumentation that can see the opposite, which is you excite the electron, you know, through some means, for example, again, running electricity through it, and then you watch it relax back down through what's called emission. Okay, so we can see both photons being absorbed by atoms and photons being emitted by atoms. And it just has to do with whether the electron is being excited, promoted up, or whether it's relaxing and coming back down. Okay. For hydrogen in particular, what was found was that if the final value was n equals 2, so this, let's just use a different color. This would be the final energy level that the electron relaxes to. And it started out at either 6, 5, 4, or 3. These were the initial. That these would emit photons that actually fall in that visible spectrum. Okay, so if I'm going to sort of just go back to this line graph here that I said was for hydrogen, you see these 4 lines. They correspond to relaxation from one of these different, either n equals 6, n equals 5, n equals 4, n equals 3, to a final value of 2. Any one of those relaxations will emit a photon in the visible spectrum. Okay, so that was Bohr's big contribution, was he took this idea of photons, took these line spectrum that they had seen experimentally and said, oh, I see what's going on here. The reason that these discrete frequencies are being emitted is because these electrons are at different energy levels. Okay, so maybe one type of problem that could be asked is, given these different transitions, which one would you expect to emit visible light? All right, and so for this, again, you got to know that if n equals 2 is the final, and n equals 3, 4, 5, or 6 is the initial, this will equate to visible light being emitted. So out of which one of these options does that that satisfy? Well, so it's not going to work for A. If you're going from 2 to 3, that's going the wrong direction. That would be an absorption, but it wouldn't be an emission of visible light. From 5 to 2, this one would give you the emission of visible light. From 6 to 1, again, that it has to have 2 as the final level. So from 4 to 2, that would also have you emit visible light. And then lastly, from 7 to 2, 7's too high, so F would not work. Okay, so these guys here, and actually let me use a different color. These guys right here would correspond to the emission of visible light. I do want to say that if we went from, say, something like 6 to 1, that would still be emitting a photon. That photon would just fall outside of that visible spectrum. It'd either be too large or too small of a wavelength for us to see. The other sort of question that I could ask is, instead of emit visible light, what if I said absorb visible light? Then the rules would just switch. So again, this is emission. If we wanted to say absorption of visible light, then n equals 2 would have to be the initial value, and n equals 3, 4, 5, or 6 would be the final value. And so if we look back over our list, we could see that B would actually correspond to the absorption of visible light. Again, all these other transitions correspond to either the emission or absorption of a photon. They just would fall outside of the visible spectrum. All right, so then what did Schrodinger do? Schrodinger came along, you see, not that much longer after, sort of after quantum mechanics had really gotten birthed, and came up with this idea that instead of treating the electrons as kind of like marbles or these hard, fast particles, we're going to talk about their position as if it was a probability, okay? This is kind of a really hard thing to wrap your head around at this point in your chemistry career, but I will say, long story short, previously electrons were being treated like baseballs, basically, where if it started out over here and ended up over here, you could be confident that it followed some sort of path that got there. Turns out that electrons are kind of magical and they don't have to follow some sort of set path. So you could have this region where you know your electrons are over here, or you know they're over there, but there's 0% chance you're going to find them in the middle. So how do they cross that gap? That's just the magic of quantum mechanics. But that's, so quantum mechanics came along and basically said, rather than try to give you the exact X, Y, Z position of an electron at all times, let's just use a probability and say that there's a 90% chance that you're going to find it within this sphere or within this certain shape. This led to a difference where, instead of like Bohr's orbits were circular, we're going to see that these quantum mechanical orbitals have very different shapes associated with them. Again, talking about quantum mechanics at this level in your chemistry career is really hard to do, because basically the model for an atom now is a math equation that's like 4 pages long or something, right? I mean, it's a very complicated sort of thing that we're trying to condense and simplify. But yeah, there are a few takeaways that we can get from it, which are pretty simple. So again, this idea that we're not going to be able to determine the exact position of an electron, we're instead going to say it's got a 95% chance of being located within this certain sphere or other shape. And the textbook uses a sparkler as this sort of idea. If you're talking about the position of the flame of a sparkler, you could try to figure out every XYZ position of all those little things, or you could say, okay, within this circle here, 90% of my light is trapped. And that's basically what quantum mechanics does. So these are these different, what are called atomic orbitals. What an atomic orbital is an electron home. And there's a certain probability of finding that electron within that orbital. Okay, but again, I think about them as a cage, like an electron cage. So we have different shapes, okay? The first one's the easiest one, that's the sphere. And again, this sort of just gives you a little bit of an idea here. If we were to take, you know, say that like we took a camera and over time we tracked the position of the electron, you'd see that within this sphere here, it's in this location 90% of the time. Okay, so we would call this a sphere. This would be called an S orbital. Okay, S for sphere. S orbital is spherically shaped. All right, and again, what does that orbital mean? It's a cage. The electron is somewhere within that cage. So again, now we're going to learn that there are different shapes of these orbitals. First one is an S, that's the simplest. We also have what's called a P orbital. And the P is shaped like, it says dumbbells. How about the peanut-shaped P orbital? Okay, so again, these are electron cages. The electron is somewhere within that P orbital, but instead of being a sphere, this guy is shaped like a peanut. And there's actually 3 different what are called sublevels of the P orbital, which is just the different orientation. So actually this shows you more of that cloud picture here. These other 3 are these 3 sublevels. So let's just ignore this real quick. Here are my 3 P sublevels. Notice that they're all peanut shaped. The only difference is the direction that they point. One of them's pointed down the XY axis, the other one is perpendicular, and then the other one is perpendicular to that. So these are all P orbitals. And there are different sublevels. So there are 3 sublevels to the P orbital. You don't have to worry about memorizing the names PX, PY, PZ. Importantly, P orbital has 3 sublevels. And again, by sublevels, the difference between them is just sort of their orientation. The last one we're going to look at, there's actually 2 more, but we're not going to mess too much with the F ones, is the D orbitals. Okay. These D are like daisy shaped. That's how I think about them. D orbital. They're shaped like flowers, basically. And again, you can see there's multiple sublevels. So there's 5 sublevels to the D orbital. Okay, and most of them are just this clover shape pointed in different directions, right? So there's a clover here, there's another clover perpendicular, another one sort of laying perpendicular. There is one that's very different from the rest of them, and that's this guy here. So just make a note of that. It looks a lot more like a P orbital, but has a donut around it. Okay, so what are all these orbitals, right? So this just got pretty crazy pretty quickly. We were at first talking about electrons on an atom, and that sort of made sense. And now all of a sudden we've got peanuts and daisies and everything like that. Okay, so this is what quantum mechanics sort of did. That big, ugly 4-page math equation that I was telling you about theorized that electrons are trapped in orbitals, and those orbitals have particular shapes. So you could have an electron that's trapped in a spherical S orbital, or you could have an electron that's trapped in a P orbital, a peanut-shaped orbital, or you could have an electron that's trapped in a D orbital, et cetera, et cetera. Each one of these is like a home to different electrons, each one of these orbitals. We'll get to how we figure out what's what here in a second, but that's the real takeaway from this particular lecture is Schrodinger, Bohr came along and theorized that the electrons have different energy levels associated with them. Schrodinger came along and complicated the crap out of everything and theorized these different shaped orbitals. And then, again, there's this big ugly math equation to back it up. Okay, and this is legit. Turns out to be the fact of the matter. So this is what we're going to take and run with. In the next lecture, we'll figure out how to take an atom, say carbon, and figure out exactly the type of orbitals that all its electrons live in.